The James Webb Space Telescope has exciting news again. A study found evidence of the first stars, 1,000 to 100,000 times more massive than the Sun. The most massive star we know of weighs 250 times the Sun. These massive stars have core temperatures 5 times the Sun's at 75 million degrees Celsius. JWST discovered these massive first stars in one of the most distant galaxies while looking at the edge of time in the early universe. This remarkable study could reveal the cosmos's origins and the last unexplored period in cosmology's fascinating history. How did astronomers discover this exciting thing? How did they calculate these extraordinary stars' masses? Finally, and most importantly, how will this discovery help us understand the universe's birth? The universe's first billion years after the Big Bang are still mysterious. It has many mysteries that astronomers are still solving. The universe was dense and hot during this time, packing all matter and energy into a tiny space. Fundamental particles emerged as it cooled, and primordial nucleosynthesis produced deuterium, helium, and lithium nuclei 10 seconds to 16 to 20 minutes after the Big Bang. As the universe cooled 380,000 years after the Big Bang, early nuclei combined with electrons to form neutral atoms through recombination. Before recombination, the universe was too hot for light. This critical event released photons from thermal equilibrium with matter, making the universe transparent. The cosmic microwave background, CMB radiation, was emitted during this time. After the CMB was released, the Dark Ages began, when no stars or galaxies existed. This 100 to 300 million year period is poorly understood. Gas clouds collapsed, forming the first stars and galaxies. These initial stars emitted energetic ultraviolet light, and supernovas and hypernovas released other radiations. Reionization of hydrogen began when these energetic processes heated the neutral hydrogen gas. This transformation made the universe transparent to ultraviolet light by removing neutral hydrogen gas clouds. By about 1 billion years after the Big Bang, the universe was a bustling place with bright stars and galaxies, like a cosmic zoo. The Dark Ages, first star formation, and reionization timelines are still being studied, but the best model of our universe's chronology is based on observations. The James Webb Space Telescope has increased the suspense of our understanding of the early universe. The JWST has revolutionized our understanding of the early universe by peering into regions of the sky inaccessible to the Hubble Space Telescope. Webb discovered fully evolved galaxies at very high redshifts, about 200 million years after the Big Bang. This discovery raises two major questions. First, what early universe conditions are missing from our models that accelerated these galaxies' evolution and growth? This leads to the second issue, the birth of stars. Forming around or after 100 million years after the Big Bang? If not, what special properties of the universe caused fully evolved metal-rich galaxies to form early on? While studying high redshift galaxies, some scientists thought outside the box after Webb discovered it. The study challenged the nature of the first stars and their role in high redshift galaxies in a novel way. This line of thinking led to this research, and the James Webb Space Telescope's observations provide crucial insights into the early universe. The James Webb Space Telescope observed GNZ11, a distant galaxy in the high redshift universe. One of the most distant galaxies is GNZ11, which existed 440 million years after the Big Bang. Its light traveled 13.3 billion years through expanding space to reach us. Remember that the Hubble Space Telescope discovered GNZ11 in 2016. The spectrum of GNZ11 was strange when astronomers observed it with Webb. The galaxy's interstellar medium had an unusually high nitrogen-to-oxygen ratio. Astronomers are curious about the abundance ratio. Why? What does it mean? The abundance ratio, the logarithm of the ratio of two metallic elements in the star to their abundance in the Sun, is a key indicator of a star's chemical composition. For instance, the abundance ratio of iron to hydrogen is the logarithm of the ratio in a star compared to the Sun. Since stars produce different chemical elements through different mechanisms, these abundance ratios can help astronomers understand the star's origin and evolution. The abundance ratio also reveals the star's age and core temperature. A famous example is the late 2019 Great Dimming of Betelgeuse. It lowered the star's temperature by 80 Kelvin. The drop in temperature was determined by analyzing the vanadium-1, iron-1 spectral line ratio, which had increased by 1.9. This temperature drop was confirmed by studying the red supergiant's infrared spectrum. What does GNZ11's high nitrogen to oxygen ratio indicate? The unusual abundance ratios in GNZ11's spectrum can be explained by globular clusters, ancient, massive, and densely packed groups of stars that formed in the early universe. These clusters are found in the halo and bulge of spiral galaxies like the Milky Way and most galaxies. Andromeda, our spiral neighbor, has 300 globular clusters, while our galaxy has 150. Scientific evidence suggests that most stars in these globular clusters were formed by mixing gas with hot hydrogen and other chemical elements expelled by short-lived older stars' explosive deaths. Older stars, called polluters, release heavy metals into the surrounding gas, enriching it and enabling star formation. This has been seen in Milky Way globular clusters. Astronomers wondered if high redshift galaxies exhibit the same phenomenon as globular clusters. This led them to investigate the polluters responsible for the high nitrogen to oxygen ratio, indicating nitrogen. To produce nitrogen, a star must fuse hydrogen into helium in the CNO cycle, which requires temperatures of several tens of millions of degrees Celsius. These conditions can only be met by supermassive stars 1,000 to 100,000 times the Sun's mass. These supermassive stars are thought to form in early universe globular clusters, where 1 million stars rapidly accrete gas and dust. This accretion causes stellar collisions, forming massive stars. In-depth studies showed that abundance ratios in globular clusters and the high redshift galaxy GNZ11 support this supermassive star formation scenario. This suggests that supermassive stars pollute both globular clusters and GNZ11 with heavy elements like nitrogen. Astronomers also consider Wolf-Rayet stars, especially those with massive star winds, potential polluters in GNZ11. This scenario eliminates the need for supermassive stars because rotating massive stars' winds are mostly hydrogen-burning nitrogen and oxygen. The analysis suggests that GNZ11's rotating massive stars' winds may explain the unusual abundance ratio. Note that this explanation only applies for a limited time. While the likelihood of rotating massive star winds polluting GNZ11 is low, astronomers cannot rule it out. JWST observations have revealed new supermassive first star scenarios. This has improved our understanding of the early universe and first stars. Webb made one more possible discovery you should know about. In addition to supermassive stars, Webb found early dark stars. Dark stars, formed at the centers of protogalaxies with a mix of dark matter and ordinary matter, annihilate when dark matter particles collide with their antiparticles, releasing energy. This new study shows that dark stars use heat energy from dark matter annihilation instead of nuclear fusion. Dark stars are mostly hydrogen and helium, with only 0.1% dark matter. As they grow, these stars accumulate matter from their surroundings and become supermassive dark stars with masses up to 1 million suns and luminosities over 10 billion times our Sun. After their lifespan, these supermassive dark stars may become supermassive black holes in our universe and distant galaxies. Astronomers found 3 dark star candidates by studying the fluxes and spectral properties of high redshift galaxies observed by the James Webb Space Telescope. Dark stars have a helium isotope absorption line that distinguishes them from early galaxies. The discovery of this spectral line in any of the 3 candidates will launch a new era in astrophysics and shed light on supermassive black hole origins. This concludes Sunday Discovery Series Episode 7.